continue. So now we've played with our digital IOs, turning on LEDs, reading switches, and that's never going to end. The digital IO, and you know, what do all Raspberry Pis have? What do all Arduinos have, right? A way to set up a digital IO to do different things, okay? We're going to be finding that we're going to be driving motors with what's called PWM. We're going to be reading sensors over serial ports. But yes, we'll be getting to all these different peripherals. And today we're going to start into the PWM, pulse width modulation. But turning on and off a digital IO is going to be in each of these labs. Okay? So for example, when we get to the serial port labs, yes, we're going to communicate between our F28379D processor and some sensor board or some sensor chip through a serial port. And we'll talk about what's a serial port. But through a serial port. But not only do we communicate through a serial port, but we also may need to turn on the chip or flag the chip saying, hey, I'm talking to you. And so this, hey, I'm talking to you, sometimes is done with an I/O pin. Exactly the same way you turn on and off an LED. So the same way you set it high to turn on an LED and set it low to turn off an LED, you, in future labs and future work, outside of this class too, you'll be using digital IOs to maybe turn on a chip and say, hey, wake up. I want to talk to you. It's called a chip select. And that's done many times with a standard GPIO. So don't say, okay, we're done with these GPIOs and all right, now we're on to the next thing. GPIOs will stay with us the whole way through this whole semester. Okay? So you'll hear me many a times say, turn on and off that IO pin just like you did an LED. Okay? So you'll hear me say that. Same message. How do we do that? We find out which GPIO it is. Maybe we connected that chip select to GPIO what? 67. I'll pull it out of the air. Okay? So then we know we would have to do GPI. Well, you know, how would you remember to do it? Let's think. If we're in CoComposer, let's say we need to talk to GPIO 67. So what's the way to do that? Well, we know all our GPIOs, right? GPIO DAT regs. Is it data regs? No, I think it's DAT regs. Am I going to be right here? Of course not. Data regs. Yeah, hey, you got it right. So remember that. You see, this is a beautiful thing about CoComposer. One thing, of course, you got to figure out what the name is. Well, where do you find that? Go look in other example code. Go look in that ledpatterns.c or whatever. Remind yourself. Always remember, and these are great things for the how-to document too, but always kind of be reminding yourself with example code. Don't think you have to figure it out without example code. Go back to the code you wrote. And remember, you know, all your projects are going to be over here in the left. So go back to lab 2 and remind yourself, oh, that's how I turned on and off that LED, right? Type of thing. Okay? Don't forget that. Don't forget to go back and look. But then again, all right, GPIO data regs, and then here's all the different GPIOs, the registers, and remember GPA, clear, set, DAT. Those are for IO pins 0 through 31, GPIO 0 through 31. GPB DAT is for GPIO, 32 through 63. See what I'm doing? So this 67 that I just pulled out of the air, if I want to set that high or low, it's going to be in GPC DAT, isn't it? Okay? So let's do that. GPC, and let's say we want to set it, whatever. Dot, bit, dot, and then here's 67, isn't it? Okay? And then what? We would set that equal to 1 or set it equal to 0 if we want to set it high or low. Good. So just to remind you about that. Now notice, let's say you cut and paste this. This is also something, maybe you've seen this. Control C. you cut and paste this and you say, well, I want to do the same thing for a GPIO 56. Now, look what happens here. Do you notice, can you see in CoComposer that GP set, C set bit is blue, but this guy's black? That means it did not find 56 in this dot bit part. Okay? So that's one way you can see, oh, I got a mistake. Or you compile it and it tells you that, it doesn't know what that is either, right? It would give you an error when you compile it. But those are kind of little neat things to watch in CoComposer for your different variables. This will scare you. If you go to, well, not that much, but EPWM, let's see, it's EPWM regs. No, I want to do 12 regs. This PWM we're going to be looking at. Look how many registers this guy has. No, what did I do wrong? Regs, did I not get it right? Is it capital? I bet it is, yeah, capital P. See, I'm guessing. I should be going and looking at example code and not sitting here guessing. There he goes. But now look at all these registers that we got to get into. Oh my goodness. Actually, we don't. That's the good news. There is a bunch out here, okay? What do we got down here? There's even more. Yeah, it just repeats. But anyway, so we're not going to have to deal with all these registers. Thank goodness. And that's why I create for you a PDF file called what I'll be calling the condensed reference. I go through the pages of the reference for the PWM and I delete some pages that we're not going to need. And you'll see in a second that I give you this condensed version of it. Okay? All right, so we'll get to that. But before we get to PWM, we got to think of another concept here. And this is, let's go and I'm going to again draw my big square, right? This is the processor. This is that black chip on your red board. Okay? And we talked about last time, there was all sorts of things inside this processor. So, we're going to be talking about PWMs. There's actually, I believe, I use up to 12. I believe there's 16 possible to come out in this. That's a number I can't remember, but definitely, let's just go with the definite number. There's 12 PWM devices, and each of those PWMs have up to 6 outputs that you can use. Anyway, we're going to just be talking about 4 outputs per PWM. But in other words, what does that give us? Let's say there's 6 per 12. Already we've got pins, right? 6 times 12 pins, 72 pins, if we were going to use all those PWMs to get out to the world. Okay? Then there's analog to digital converters. There are these serial ports. Serial ports, SP, we got SPI, we've got I2C, we've got UART. If we get even deeper, now we won't get into this, but there's peripherals for talking to an SD card. Okay, so you can plug in a little flash SD card into this guy if you set it up right. Our board does not have that. The red board does not bring out the pins to an SD card. Okay. Let's see, what else can we do? We can talk to external memory. We can just general purpose digital IOs also. So a lot of different peripherals that use a lot of different pins. All right, and if I'm not mistaken, let's actually check. I always say 357. Let's see if I was mistaken on that. So if we go to the data sheet, so by the way, in your repository, okay, you would have it in whatever you renamed lab repo to. There's a number of documents in here. I put a lot of these documents up at the website, but you can also always go to your repo to find these. And the 2 most important ones down here is the data sheet for the 28379D and the tech ref. Okay, and as I said, what I'm going to do in my condensed references, I'm going to pull pages out of the data sheet and pull pages out of the tech ref and put it together for a little more condensed reference for you guys. Okay? Why? Look at this. If I go, let's look at the data sheet. And how many pages? It's 226 pages. And then if we go look at this, I think I already got the tech ref up. Yeah, the tech ref, look at this, 2,800 pages, okay? No, we're not going to be reading through all 2,800 pages of this thing, okay? But all the peripherals, see here, it's really nice, you have a chapter for each peripheral here. So all the different peripherals possible for this type of chip. So for example, this, you know, you got to be careful too. The sigma delta, oh, that's the filter, never mind. Yeah, all devices have this. Anyway, sometimes TI will create tech references, and depending on the part number of your part, you may not have some of these peripherals in there. With this one, the 379D is kind of like their super chip, and it's got all the peripherals inside of it. Okay, so it's got all that are listed here in the tech ref. So anyway, I'm going to try to condense and pull out the parts that you need of this, but still, you'll probably throughout the semester need to reference this technical reference. And again, probably best to pull it up in Acrobat, so you do see all the chapters over here on the left, right? So you can easily go find what you need. Well, I wouldn't say the word easily, but you can find a chapter at least that you need for the certain peripheral you're working with. Okay, so we are going to be digging through data sheets and references, and it gets confusing. It's very confusing reading through data sheets. When I get a new part, a new peripheral, I'll read through the data sheet, and myself, because I've been doing this for a long time, I can say, well, yeah, I know I'm not going to be doing that, so I can skip that part of the data sheet, skip that part of the tech ref. I'm going to try to be giving you a little bit of that information as we go through. But you read it, maybe you think it's going to work this certain way, and so you try it out. Doesn't work with your processor or the peripheral, you got to read it again, right? And it just, you read and reread these things. Now, you have the advantage, you can read it and say, Dan, I don't understand this at all, right? I can maybe help you out. That's a nice thing in this class. But if you're out there after this class, you know, just know that I don't read the data sheet once and know what's all going on, okay? Know that that doesn't happen, all right? You read it and think, oh, okay, this is how the software is going to go. This is how we should set it up. Run it, and it does something a little bit different than you think. You're like, what's going on? You know, and this grinding back and forth, reading the data sheet back and forth to the device, it may take you a couple weeks to really figure out what's going on. I don't know, it depends how much time you have to work on it, right? Sometimes it's also good to just kind of put it away for a little while, all right, and then work on something else, and then come back, read the data sheet again, and then see where, you know, maybe where you made the mistake or something you missed in the data sheet, something like that. Anyway, all I'm trying to get you to understand is it does take a little bit of time understanding these data sheets. Now, maybe you don't find it all in the reference manual either. Maybe you go, remember where Lab Starter is, remember there's a load of example code in there. Remember, that was the reason I put Lab Starter in that spot in C2000ware, because all the examples are there. So the other place you go, you read the data sheet and you go look at the example C code, right? That's also really good. Every once in a while, TI will also create some white papers, they call them, on different peripherals on how to do things. And one last thing, I mean, there's more, but one other thing that is helpful, and you'll see it's in the, now again, probably not for during this class time, but maybe if you have time to read through this. But you notice here, there is a workshop that TI trains people with. A 1-day workshop and a 4-day workshop. And those notes, those slides, the presentation and the labs they do, they actually, you know, rent a hotel, you know, whatever, a conference room, and have computers set up with our red boards, and they run through a little bit of coding labs. So this is another place to find, this is all in your repository I put there, another place to find some good details on this processor, especially when you get out of this class, okay? Or we get to the final project or something like that this semester. See where I'm going? Anyway, just kind of talking a little bit about this data sheet, and I'm not saying it's going to be easy the first time you start reading through it. Okay, So good. Now, in addition, okay, what do I wanted to look at the data sheet and find how many pins. I kind of guessed a little bit on the 357 pins. Let's see, where would that be at? So in the data sheet, yeah, 337. I was close. I was close. So the package that we have is the ball grid array. Remember I talked to you about that? On the bottom of that black chip, on our processor chip, there's a bunch of balls, 337 of them. Okay? And they get plopped in the right place on your circuit board, the red board, and then get baked on. And that's how it's soldered. Okay, those balls at the bottom. And that's what that BGA, ball grid array, stands for. You can also buy this chip in a 176 pin version and a 100 pin version. Actually, I've built some boards with the 100 pin version because I can solder that. What that is, those pins are all sticking out the sides of the chip. Similar to, you know, the little chips you had pins sticking out, the surface mount pins sticking out one right and left side, right, of your chip. Well, this guy, the 100, has 25 out the top, 25, 25, and 25 out the back. And then you can line that up on your board and solder that down. But of course, when you get to this 100 or even the 176, a lot of the pins, you won't be able to access, for example, 12 PWM channels, maybe, or well, what am I trying to say? If you're going to use the channel A and channel B of all 12 PWMs, you're talking about 24 I/O pins. So you've already used up, a quarter of all the pins that you have coming out. And remember too, these 100 pins, some of those are power and ground, not just your output and input pins. Anyway, but anyway, on our red board we have 337 pins. So that's great. So now, and the other thing, I always get excited about this when, I'm a junkie for these new processors and everything. So when TI comes out with a new version of this kind of processor, other kinds, I'm always, digging through and reading the first part, all the different peripherals it's got, capture inputs, quadrant encoder inputs, pulse width modulation, look at all this. But now when you see all these parts, all these different peripherals, you've got to remember that you cannot necessarily get all of these at the same time out through your I/O pins. There's a multiplexing going on inside the processor that each pin has up to, now most of them are only about 6 options, but they have it set up for maybe future chips that there's a possibility of 16 different options going out of one pin. And so I sit down when I get a new processor and deciding, well, how am I going to build my green board, right? I'm going to set it up. What am I going to use each of the I/O pins for? So I print out this multiplexer table, and you're going to see it here in just a second. And I start highlighting, okay, for this I/O pin, I'm going to use for the quadrature encoder. This I/O pin I'm going to use to turn on LED 6 or whatever. You have to kind of figure it all out and make sure you have enough I/O pins to do everything you want to. So what am I getting at there? So let's look at this. This is at the website. Let's go look. And so we'll be looking at this guide for throughout the rest of the semester. So I put it here under Lab 3, which we're working on this week, PWM. But it's this guide here. Now I created this for you kind of from TI's PinMux. They call it a PinMux, from its PinMux table in the data sheet. Okay, but for example here, let's look at it. So our pin GPIO. Let's see where's one for LEDs. So for example, LED 8 is GPIO 25 here. Okay. That just happened to be what I chose, okay, by thinking about all what I wanted to do with the board. But not only can it be GPIO 25, we can also change the mux such that it's this out X bar. This has something to do with signaling, so don't worry about that. But it also could be EQEP, 2B. It can be a serial port pin. This is for what's called the McB, multi-channel buffered serial port, anyway. It can also be an SPI pin. And remember how I said you could connect a SD card, you know, one of the little micro SD cards to this board? Notice here, all these I/O pins, if we decided we needed that SD card, we could use those I/O pins to actually write data to an SD card. Okay? But yeah, there's so many pins needed for an well, yeah, I guess. I don't know, I haven't played with this SD card. It takes up a lot of I/O pins, so it's got to be really important for us to use that, right? Because now we can't use some of these other features if we're decided to use these pins for an SD card. All right? There's actually, the reason I also don't use an SD card, there's a way to communicate with an SD card over the SPI serial interface. So you can't, so you don't need to use these. This is much faster though. This would be a fast bus SD card. Anyway, so that's just an idea of the MUX. So you will, at the beginning of labs, you're going to say, or I'll tell you, we're going to need to use EPWM 2A and 2B. We're going to need to use, let's see, SPI pins, SPI-A clock, SPI-A data, or actually it's called master in, master out, all this stuff. We'll get to those serial port pins. And you'll have to say, and I'll say, well, and I'll give you a little tips, of course. We'll be using GPIO 29, say, for the UART's transmit data A pin, or something like that. And you will then, in your C code, have to set up that data pin as that function, which, if you go up the bar, that is option 1. Okay? So we have these options, option 1, 2, 3, 4, sorry, 4, no 4. 4, it's funny, I don't know why, but they reserved for now, if you set the option to 0, 4, 8, or 12, it's set up as the GPIO pin. And by default, when you power on the processor before any program's loaded, the default MUX is 0, set up as the GPIO pin. Okay? But then we have option 1, 2, 3, 5, 6, 7, and then notice how 9, 12, 13, 14 are kind of all reserved. Right now, TI is not using them for anything. Maybe in future processors, they will. A lot of times you'll see that. You'll see a lot of reserve space when we're talking about registers. So you have this register, and then right after it, TI calls it a reserved register. Okay? It just means maybe in future, because what TI tries to do, and one of the reasons I stick with Texas Instruments too, and most companies do this, you know, the next chip that they build has a lot of the same peripherals that the earlier chip had, right? And so programming that is you know, a little bit easier because you've already done it for a previous version processor. And so, but then what they do is when they come up with this new chip, maybe they want to add this new peripheral, or they use that reserve space to add registers for that peripheral, if that's making some sense. Anyway, okay. So your job will be to figure out what mode, what MUX state your pin will need to be in. So if you go to our C code, beginning C code, you'll notice that all these lines of code here, I am setting up right here the PinMux. These, we have a bunch of them. A lot of these are our LEDs, but you'll notice, let's see, do I have any of them? No, they're all set up right now as LEDs. But let's say GPIO 25 right here. So this is, we just talked about it, didn't we? LED 8. So here's this GPIO setup PinMux, etc. right here. Okay? Well, again, if we go to the PinMux guide and I tell you 25, well, let's use a different one. Let's do 27. So we go back here and GPIO 27, let's say we want it to be SPI's, this is actually its chip select. So we would change this then to be option 6. So it's as simple as going to your C code and changing this number 0 to 6. Okay? And by doing that, you have set up, Now that pin is no longer GPIO 27. And LED 10 will not go on and off like you've programmed it to. Okay? Instead, it will be used by the serial port peripheral. Okay? The serial port peripheral has complete control over it. Okay? The only other option you have after you set it up as a serial port pin, you do have the option to decide if you want the pull-up resistor attached or not attached. Remember we talked about this little pull-up resistor that's inside the chip on all the I/O pins? That way, when we put it to a passive push button, the signal's not floating, it's pulled up. And again, where to use that, I usually find that in TI examples, and you'll see that. You'll see even in this week's lab, they recommend that we we disable the pull-up resistor when we set up a pin as PWM. Okay? All right. Good. And so there we go. So that's what you have to do, and then you could set the pin options to say no pull-up. That would be another option. Where's that at? Here would be, see down here where we set the option for inputs. We could change that right, where's it at? Down here. We could say, let's see, what is the option? So right here, GPIO pull-up. That enables the pull-up, and if we go to open declaration, there is input, push, pull. Oh, okay, yeah, sorry. So by putting it into push-pull mode, you are disabling the pull-up resistor. Is that true? I think so. Yeah. Open drain. Right. Right. It push-pull, and then I would also disable because that's left shift by 0. Yep. So that would turn it. That would disable the pull-up resistor. So if I go back to here and I set this GPIO 7 to push-pull instead of GPIO pull-up, then the I/O pin would not have its pull-up resistor enabled. Anyway, okay, good. All right, so so you'll see in the labs. I'll ask you to go to the PinMux table, and that's that sheet that I just showed you to figure out. And that's what you always should do. Each lab you should kind of just remember that, okay, we're going to be working with these I/O pins as I start talking about them in the lab. We need to make them in the options, put them in the setting that is needed, like when we get to the serial port setup and all that kind of stuff. Okay, so that'll definitely be something you'll be doing by the end of the semester in your final project, because you'll choose to use this sensor instead of something else, and you have to set up your I/O pins to actually communicate with that sensor. Okay. All right. So that's the PinMux table, and we'll